Hello everyone, this is Dilip Chakravarti, belonging to Cyber Security Department, working as assistant professor in Institute of Aeronautical Engineering. So today we are going to discuss about AVL trees. So in the previous sessions we discussed about binary trees, binary search trees. Uh, let's see about AVL trees. As there are some drawbacks in binary search trees. If you are continuously adding a greater element, so you will form a right skew tree. Or if you are continuously adding a smaller element, you'll form a left skew tree. Okay, so where you need to process many number of levels for searching an element. Okay, it's a drawback of binary search tree. So we got a new concept where we need to balance the height. Okay, we need to reduce the height. So we call these trees as height balance trees also. So let's see it. Uh, so AVL trees was introduced in the year 1962 by Adelson, Welsky, and Landis. So AVL trees are developed by these Adelson, Welsky, and Landis. An AVL tree is a balanced binary search tree in an AVL tree. The balance factor of every node is either -1, 0, or +1. Okay, we are going to calculate the balance factor for each and every node. Okay, so it must be either -1, 0, or +1. Okay, how we are going to calculate the balance factor? That is main point here. Balance factor of a node is the difference between the heights of left and right subtree of that. Okay, we are using a formula: height of left subtree minus height of right subtree. We are calculating the height of left subtree and we are calculating the height of right subtree. We are finding the difference between these two things. Okay, so if the difference is -1, 0, or +1, we'll say it as AVL tree. Otherwise, we'll say non-AVL tree. Okay, we need to make any tree as AVL tree. Okay, AVL tree is a height balanced binary search tree. That means an AVL tree is also a binary search tree. It is also a binary search tree, but it is a balanced tree. Okay, so we are whatever the steps, whatever the things we have seen in binary search trees, all comes here also in AVL trees. Okay, AVL tree we can say it is also a binary search tree, but here we are maintaining the height. Okay, so it should not be more than these values. Okay, it should be in between -1, 0, and 1. The difference between the height of left and right subtrees of every node in the tree is either -1, 0, or 1. Okay. In other words, a binary tree is said to be balanced if the height of left and right child of every node differ by either -1, 0, or 1. Okay, of course, all the things are same, which is explaining you about the height only. Okay, we are just calculating the height of left subtree and the height of right subtree, and we are finding the difference. In an AVL tree, every node maintains an extra information. So we are maintaining an extra information. We call it as balance factor. Okay. So observe here. This is an AVL tree. For each node, I'm giving some values. Observe here all the values. It may be either 0, 1, or -1. Okay. So how I am getting these values means I'm calculating the height. Observe for 25. The height of left subtree is 1, 2, 3. Okay. So one edge, two edge, and three edge. So height is 3 in the left subtree, and right subtree is 1, 2, 3. Okay. Totally 3 minus 3, you will be getting it as 0. Okay, so in this way we are going to calculate the balance factor. Observe for 1, The balance observe for 20, the balance factor is 1 2. Left is left, we got 2, and right we got only 1. 2 minus 1, we'll be getting it as 1. Okay. See, for 36, it is left is 1 2, and right is 1 2. Okay. So 2 minus 2, you'll be getting it as 0. So observe for 10. So as there is no left child, so it is 0. Okay. So there is one child for right side. So 0 minus 1, you will be getting it as minus 1. Okay. So for 22, as there are no children, so left minus right, as there are no children, we'll be getting it as 0. Okay. For leaf node, always it will be 0. Okay. So as there are no children, it is always 0. Okay. Observe for each. For this one, see, observe for 30. It is having only one left subtree, but it is not having a right. That means 1 minus 0 will be getting it as 1. Okay. So all the nodes are satisfying the balance factor. All the nodes are, it may be either 0, 1, or minus 1. Okay. And every AVL tree in a binary search tree, but every binary search tree need not be a AVL tree. Okay, the same what we have seen in binary search trees. There we said that every binary search tree is a binary tree, but every binary tree is not a binary search tree. Similarly, here every AVL tree is a binary search tree, but every binary search tree need not be a AVL tree. Okay, so I will see some other examples of AVL trees. Observe here, I'm calculating the balance factor. So this side only 1, this side it is 2. 1 minus 2, will be getting it as minus 1. Okay, here he considered, in this example, he considered right minus left. Okay, that means he considered like this 2 minus 1, which is 1. Okay, so here also 1 minus 0, which is 1. Okay, here as this one is leaf node, will be getting 0. So here also 0. So here 1 minus 0, it is 1. Okay, this is an AVL, not an AVL. If you observe here 1, 2, 3, 3 minus 1, yeah, we will be getting it as 2. It's a violation. Okay, so as there are 3, we'll be getting the value as minus 3, minus 1 will be getting as 2. Only the value should be allowed are 0, 1, minus 1, but 2 is not allowed. Okay, so this is not an AVL tree. Okay. What are the operations we are going to perform on AVL trees? I can perform either insertion, deletion, search. Okay, insertion in an AVL tree is performed in the same way as it is performed in binary search. See, we are inserting the element as similar to the binary search trees. Okay, but the only thing is we need to check the balance factor. If it is violating that balancing, we need to perform some rotations. Okay, we will see all those things clearly. Okay, then deletion also we can perform in the same way as it is performed in binary search trees. Deletion may also disturb the balance of the tree. Okay, therefore various types of rotations are used to rebalance the tree. So similarly, searching, finding the location of some specific element in an AVL tree. We'll see all those things with an example. After performing any operation on AVL trees, the balancing factor of each node is checked. There are following two cases. Okay, after the operation, the balance factor of each node is either 0, 1, or minus 1. In this case, the AVL tree is considered to be balanced. The operation is concluded. After the operation, sometimes the balance factor of at least one node is not 0 or 1 or minus 1. It may be change. Maybe it is more than those values, okay, or less than the zero or less than the minus one. So then we have to we will be getting an imbalance tree. We have to perform some rotations, and we need to make the tree as AVL tree. We need to make a balanced tree. Okay, by using the rotations, will be balanced. In AVL tree, after performing operations like insertion and deletion, we need to check the balance factor of every node in the tree. If every node satisfies the balancing factor, if every node satisfies, no problem, then we can conclude the operation. Otherwise, we need to balance it. If we get an imbalance, we need to rotate. Okay, rotation is the process of moving nodes either to left or to right to make the tree balanced. Okay. Uh, there are four rotations, and they are classified into two types: single rotations and double rotations. Okay, in single rotations, we are having LL rotation and RL rotation. Left to the left subtree, right to the right subtree. In double rotations, LR rotation and right left rotation. Left to the right subtree and right to the left subtree. Okay, these are the different rotations we have. Okay, if a tree becomes unbalanced, when a node is inserted into the right subtree, then we perform a single left rotation. Okay, observe LL rotation is anti-clockwise rotation. Observe here, I inserted 1, 2, 3. First, I have taken 1. As 2 is greater than 1, I am inserting to the right. As 3 is greater than 2, I am inserting to the right. I got a tree like this. Okay, now, if you observe, if you are calculating balancing factor for each and every node. So for this one, you got 0. For this one, 0 minus 1, you'll be getting minus 1. 0 minus 2, you'll be getting minus 2. Okay, so here an imbalance occurred. Okay, so as we are adding, uh, okay, it looks like of course it looks like right to the right child. So if you are looking a mirror image, so at the screen side, this is the left to this one, and this is the left to this. Okay, so I need to perform a rotation. Okay, we call it as a LL rotation. Okay, anyhow, we can name it as for naming convention, we can say it as RR rotation. Okay, so what we need to do is we'll perform one rotation. So here, here first I need to perform this. Here I need to perform this. I'll be getting one rotation like this. So 2 comes in the middle, and 1 will be coming to the left of 2, and 3 will be coming to the right of. Okay, so this is one thing, and AVL tree similarly, we can consider like this. C3, the left value 2 I inserted, then 2 I inserted 1. So I got a balancing factor of 2 here. Okay, so 1, 2, 2 minus 0, I'll be getting 2. So as I got imbalance, I need to rotate this. Okay, so I simply rotate this like this. Okay, 2 comes in the middle, and 3 comes to the right. Okay, see, observe here, 2 comes in the middle and 3 comes to the right, like this. Okay, this is another rotation. Then LR rotation. Observe here. So for the left subtree, I'm adding element 2 as a right subtree. Okay, so LR. So what I need to do is I need to perform 2 rotations. So the LR rotation is a sequence of single left rotation followed by single right rotation. So I am going to perform a single left, then single right. Okay, observe here, if this is the tree, so as I got imbalance, so 1, 2, 2 minus 0, I got here as 2. So mm, here I need to perform the rotation. So in the first rotation, 2 comes here and 1 comes as a child to 2. Okay, see observe here. So 2 comes here, 1 comes as a child to 2. Okay, then I need to rotate again. So this is one rotation and another rotation. So if I'm performing this rotation, so 2 comes in the middle and 3 comes to the right. Okay, so in this way I'm inserting the element. Okay, so just first I rotated this one, so the diagram becomes like this, then I'm rotating like this right side. Okay, so it comes like this 0, oh sorry, 1 2 3. Okay, read the search element from the user, compare the search element with the value of root in the tree. If both are matched, then display given node is found. Okay, if both are not matched, then check whether such element is smaller or larger than the node value. You are just performing the search. It is similar like binary search tree. If search element is smaller, then continue the search process in the left subtree. If the search element is larger, then continue the process in the right subtree. Okay. Now we are going to repeat the same procedure until I found the element. If I found the element, I'll make it as successful, or otherwise I'll say element is not found. Okay. So now AVL tree insertion. Okay. So we are following some steps here. In an AVL tree, the insertion operation is performed with order of log n time complexity. Time complexity for performing insertion operation is the order of log n. In AVL tree, a new node is always inserted as a leaf node. I'm inserting a new node as a leaf node. Okay, step one, insert the new element in the tree using binary search tree insertion. So by using BST logic, we are inserting the element. Okay, so if the element is greater than the root element, I'm moving to the right side. If the element is less than the root element, I'm moving to the left side. Okay, whatever we have seen in binary search tree, we are implementing the same thing for inserting an element in AVM. After insertion, I have to check the balance factor. Okay, I have to check the balance factor of every node. If the balance factor of every node is 0, 1, or -1, then no problem. Okay, we will go for next operation. If the balance factor of any node is other than these values, so then the tree becomes imbalanced. I need to perform rotations. Okay. After inserting an element in existing AVL tree, balance factor of only those nodes will be affected that lies on the path from newly inserted. Okay, so wherever you have inserted, so in that path only you'll be getting the you will be finding the balance factor which may be effective. Okay, so rule 2, check whether the AVL tree is still balanced or not after whether it is balanced or not after the insertion. I need to check. Okay, there is no need to check the balance factor of every node. Check the balance factor of only those nodes that lies on the path from newly inserted node to the root node. Okay, wherever I have inserted, you there only you are going to consider the you are going to find the balance factor. Okay, and rule 3 is states like that. After inserting an element in AVL tree, if tree becomes imbalanced, suppose if it becomes imbalanced, then there exists one particular node in the tree by balancing with entire tree. So we are going to balance that. Okay, to rebalance the tree, balance that particular node. So I need to balance that particular node so that my total tree become balanced. Okay, to find that particular node. Okay, to find that particular node, traverse the path from newly inserted node to the root node. From newly inserted node, I'm traversing to the root node. Okay, check the balance factor of each node that is encountered while traversing the path. Okay, I'm checking for each and every node in that path. I'm checking the balancing factor of each and every. The first encountered imbalance node. So whatever the node which encounters the first imbalance will be the node that needs to be balanced. So whatever the node I have observed which got imbalanced, so that node I need to balance. Okay. So what I need to do for balancing it to balance that node? Count three nodes in the direction of leaf node. Okay, then use the concept of AVL replication. So I'll be checking the three nodes. So and I'll be finding what type of rotation I need to perform. Whether it is LL rotation, LR rotation, RR rotation, and RL rotation. Okay. See, construct, okay, you will see here, we'll try to construct an able tree by inserting numbers from 1 to 8. Okay, first, nothing is there, I have taken 1 as my root node. Then 2, as 2 is greater than 1, I am taking as a right child. Okay, then 3, so I have placed. Now I am calculating the balance factors. So here, 0 minus 2, I'll be getting it as -2. Okay, so what I need to do, I need to rotate the tree. Okay, so I need to perform rotation. So 2 comes in the middle and 1 comes like this. Okay, so as this is a left subtree, left, I need to perform LL rotation. Okay, only one rotation. So 2 comes in the middle, so it is like this. So now it got balanced. Then again I'm inserting 4. So no problem here. I'm calculating the balancing factor for each and every node. So it is already balanced. Okay, there is no problem. So when you are trying to insert 5, so after inserting 5, so observe the balance factors. So here I got -2, here I got -2, -1, 0. Which one I need to change? So as we have seen the steps from the leaf node to the root node, I need to find the balance factors. Whichever the node which got imbalance first. So this is balanced, this is balanced. So here I found -2, which is imbalance. So from here I need to perform the rotation. Okay, if you observe this one, so here I got the LL rotation. I'm just performing my LL rotation. So 4 comes in the middle, 3 comes as the left child, and 5 comes as the right child. Okay, so 4 comes in the middle, and 3 comes as the left child, and 5 comes as the right child. Okay, in this way I'm going to perform the rotation. So now I'm trying to insert 6. So after inserting 6, so I got imbalance here. I'm checking here, here, here. So I got imbalance here. Okay. So now I need to pick the rotation, what type of rotation I need to do. So here I'll be performing one rotation. See here. So here I need to perform rotation. So first 4 comes here. So let us consider this one LL rotation. So 4 comes here. For 4, the left child should be 2. Okay, so right child of 2 should be 3. So we'll be getting like this. Okay, I'm going to perform the rotation like that. Similarly, then insert 7. So tree is imbalanced here. I found imbalance here. So I'll rotate LL rotation. I'll perform LL rotation. 6 comes here, and the left child of 6 will be 5. So and right child will be 7. Okay. So I got the same thing. Okay. Now it is balanced. So now try to insert 8. If I insert 8, nothing happens. Tree is already in balance. Okay. So this is about insertion in AVL tree. I need to insert the elements like this. Okay. So then deletion operation in AVL. So far we discussed how to search an element in an AVL tree, which is same as binary search tree. Then insertion, while inserting, we got a lot of problems. We are using some rotations here. Similarly, and deletion operation in AVL tree is similar to deletion operation in binary search. But after every deletion operation, we need to check the balance factor. Okay, if the tree is imbalanced, if the tree is balanced after deletion, no problem, go for the next operation. Otherwise, perform the suitable rotation to make the tree balanced. Okay, I hope it is clear about AVL trees. Okay, thank you.